Let's get started with deep feed-forward networks. So this is an example of hypothetical sensor data of a production machine. So each row contains information about the production of a particular part with an associated part number. So our goal is to predict asperity, which is highly correlated with the fact if the part is healthy or faulty, based on the observed sensor values. So which column can be used to create a simple rule for this? First, we have to observe that all three columns are aggregations of some sort of sensor value. So we are losing information. But this is fine for this example. We notice that the vibration aggregation gives us the best indication for a rule, so let's code it. So let's start with creation of a data point. The first field is part number, so let's take 100. The next field is max temp, which we will set to 35. Then min temp is 35 as well. And finally, set the max vibration to 12. After producing the part, asperity is measured. So we set it to 0.32. So let's copy this 4 times to reflect our 4 measurements. As in the example of the slides, I will update those values now accordingly. Let's implement our simple rule to predict asperity based on a sensor value. Obviously, max vibration has the largest impact on the outcome. Therefore, if max vibration is greater than 100, we return 13 or 0.33 otherwise. If we now test this function, we get quite good results. So now let's see if we can do better without hard coding a rule. This formula here is called a linear regression model. It's called regression because it predicts a continuous value based on observations x and weights w. Let's create our first machine learning algorithm called linear regression in Python. So remember that we have to create a linear combination between our input fields and some parameters w. And if we plot this, w1 is the offset of the line. So if we run this now, we obviously run into an error because we haven't defined w yet. So let's do this now. And now let's choose the parameters w in a way that it somehow resembles the rule which we have created before. If we set everything to 0, we get 0 as a result. So let's try to adjust those values. We cheat a bit, we just take the numbers of our data set and play around until we get a better result. As we can see, we are getting relatively close here. In a real-world scenario, of course, those parameters w will be set by an optimizer, which is part of neural network or machine learning training. Maybe you've noticed that there is one x missing in order to get equal-sized vectors. Therefore, we define x0 as 1. This is the bias term or the offset of the linear regression. So now we can multiply x with w because both vectors have the same length. If we just write down what we have learned before, we will come up with the following. So doesn't look this like linear regression? Just put y at the end and you can see it. So that's cool, we can express linear regression with a single vector-vector multiplication. It turns out that paths with an asperity greater than 1 are not usable, so we consider them to be faulty or broken. Let's change our table to reflect this. Let's code it. So let's change this regression dataset into a binary classification dataset. Then our rule gets more simple and also more precise. And in addition, let's change our linear regression model to a logistic regression one. In order to achieve this, we just add a sigmoid computation step to our result. So the new result is between 0 and 1, and by selecting a threshold in the middle, so we can basically turn this model into a binary classification model. So this looks brilliant already. So the logistic sigmoid function squashes a range from -infinity to +infinity to a range between 0 and 1. So this means we can easily turn our linear regression model into a logistic regression model and create a binary classifier. Oh, let's wait. We have to define a threshold between 0 and 1 in order to get a binary classifier, in order to get a clear separation between the classes instead of a continuous range. So why am I telling you all about this in a neural networks class? So let's have a look at the most simple neural network, the so-called perceptron. The idea is that your input vectors get multiplied with a weights vector, and finally the sum is taken. Note that even the bias term is taken into the sum. So what you should be aware of is that this is nothing else than a linear combination or a dot product between two vectors, or in other words, linear regression. If you replace sigmoid from the logistic regression function with a simple step function, you are done and you have created a perceptron. A perceptron is a binary linear classifier. So now let's see how we can improve this. By the way, the first perceptron has been implemented on top of an IBM 704 in 1954, which was the first computer with floating point arithmetic hardware. So this guy here is a feed-forward neural network with a so-called hidden layer. In order to understand this better, let's code it first. So Python dictionaries are of course not the best way to do data science. Let's convert our data points to a matrix. First, we have to get rid of the labels, which are called keys in Python dictionaries. And turn each data point into an array. Neither asperity nor part number are required here, so let's get rid of those. But we have to align this array or vector to the size of the weight vector, so we have to add a 1 at the beginning in order to support the bias. So this is what we want. Native Python arrays are slow and also not supporting linear algebra operations. So let's wrap this into a NumPy array. And let's do it for all the data points. Let's create a function called neuron, which computes the logistic function for just one data point. We define a weight vector w, which we initialize randomly, and use the dot product between the data point and the weight vector in order to compute the linear regression function. Then we apply sigmoid as activation function and we are done. So let's see if this compiles and runs. Note that we don't get anything useful here because we randomly initialized the weight vector w and didn't train it. By the way, training means updating the weight vector. So now let's pimp this function a bit in order to compute all data points in parallel. First, we have to improve the sigmoid function that it also takes multiple values at once. Fortunately, NumPy does the job for us here. Since this function now takes a matrix, we also have to change our weights from vector to matrix as well. And finally, we have to create a matrix from our input data. We can use NumPy again because a nested array is nothing else than a matrix. So now we can compute one layer in one go. Now let's create a second layer. We only have to change the weight matrix because the second layer is computed independently from the first layer. And as a last step, we just stack those two computations on top of each other and we are done with our first feed-forward neural network. Of course, the predicted values are incorrect because we are using randomly initialized weight matrices. This is now an untrained feed-forward neural network. Note that a single hidden layer neural network is capable of representing any mathematical function. This is known as the universal function approximation theorem. So you might ask yourself, why are multiple hidden layer or other topologies used at all? This is because of training. Even if we can represent any mathematical function, we might not be able to train it. Because training means selecting good values for the weight matrices, and this is not an easy task. But let's talk about this later. Let's get started with recurrent neural networks.